being recorded. But awesome.
Oh yeah, all right. So everybody, you are now officially being recorded. If you don't want to be recorded, bail out, I guess. Uh,
Is the video going to be published somewhere when you're done, Randy?
oh yeah, somewhere. I'm not sure how to do that exactly, but for sure somewhere.
Okay, awesome.
Um, I had a little issue with GoDaddy, my server guys, because when I got the account, they went, "Oh, unlimited. It's unlimited." I went, "Great! I've got a crap ton of files. I'll just upload them." So I put a ton of stuff up there, and then I got a note from them saying, if you want to do that kind of file access, you have to use something like Dropbox or something like that. We will cancel your account if you don't take all that stuff off. And it kind of bummed me up. Oh, hi Seth, how are you? How come nobody has video games in the background? Wait a minute. Oh, CRTs, though, that's great. I see him, Seth. I see him. Awesome.
Yeah, that's
Oh,
definitely in the workshop there.
super. Oh, that's super.
Yeah.
Maybe you can take us on a tour later, or are you anchored to something there?
No, I'm on my laptop. This is my basement. I mostly collect black and white. I have a bunch of black and white tubes here.
Oh my gosh, are we going to talk about Motorola XM501s then?
I do okay with them. It's this little guy that I recapped, and he just let me see if I hold it. See it. Double dribble's hooked in now. It has a wave to it that's kind of subtle.
Is that a Hantrax?
It's a Sanwa V21. It's a tiny monitor. It's I don't know how many it's
Yeah, not familiar with it. Not familiar with it. I did cut my teeth on black and white. In fact, a bit of trivia, I guess, for some of you, maybe some of you know this, the very first actual Atari Pong games, they were really commercial CRT black and white, obviously CRT black and white monitors, case and all put in there, and we tapped in past what's known as the video detector. The way RF transmission works is it has a radio frequency circuit, and then it goes eventually down to something called the detector that changes it into audio and video, basically. And so we would just lift the diode right there and insert the video right there, and thus Pong was born. So there you go. 1971.
What's funny is I found a guy who has the same issue I have. I'm going to post a link in here. He also has the same. After capping his, he had the same issue, where his screen was shaking. Like a little bit of a wobble to it, I guess. And but he doesn't explain. I have to reread it. I just came across it, but I explain how he fixed it.
All right, so it's like 12:12. Lisa and Robert, you look nice and relaxed there. You settled in and everything. I mean, So maybe let's talk for just a minute about at least my intentions here, I guess, and that is, well, first of all, let me back up for a second. I really have to salute the dedication of you folks, you people, the game collector community. Hey, John, how are you, man?
Excellent, thank you.
I really have to salute your dedication, and maybe even kind of make an apology, sort of in a way. When the coin-op community was going really strong, my dedication was really to coin-op mechanics, guys that are on the route, guys that are, doing the job. And I would always welcome anybody to call me, and anytime, man, I'm happy to help any man with his job. I will, not a problem. I love doing that. But game collectors would call me, and my philosophy at the time, no longer, let me say, was, hey, that's your hobby. It's not my hobby. We're in the profession. It's your hobby. I'm not really here to service your hobby. I'm really here to help the guys that are out in the field, which of course, as you know, doesn't exist anymore. And so a bunch of time went by, and I'm still in the casino industry. I do the same sort of training, but for slot machine technicians. Also closed down now, as you know, most casinos. I wouldn't step foot inside a casino anymore, so not now. But you're welcome to go. Go, spend your money. Anyway, so a long time passed anyway. And then I was contacted by a guy named Hassan, and he runs the National Video Game Museum of the Netherlands. Super incredible. I don't know, maybe some of you know him or not. He's a super incredible guy, just so likable, and his dedication to the coin-op history is profound. I mean, it really is. And I kind of talked to him for a long time, and he said, Randy, you don't understand what it's like over here, he said at the time, in Europe. It's not like a hobby. We're really dedicated to the preservation of these things as pieces of art. And, you know, when we do a full restoration, we want it restored down to the correct screws, which I just saw recently in the group. Somebody was looking for some kind of a screw for a Konami game or something like that. And I thought, you know, it was just really amazing.
We just lost your audio.
Sorry, I accidentally hit the mute button. Am I back? Cool.
Yeah, you're good.
Okay, so but I shudder when I read some of the kind of misconceptions of CRTs and working on CRTs and the magic of the Flyback transformer and how all this comes together and kind of all that kind of stuff. So my goal, I suppose, here is to make it educational as we talk about, I guess, speculating what your specific problem is. I mean, I do refer to it as a workshop, and I suppose I want it to be. So does that make sense to anybody, everybody, anybody?
Yeah, sounds good to me.
Yeah.
Yeah,
Okay.
sounds great.
Yeah. Okay. All right. So, I mean, I'm not sure. I guess you can just speak up if you have questions or something like that. Is the person that asked me about the problem where the screen is dark on the left and bright on the right, is that person here?
That was me, Randy. Can you hear me?
Who is this?
Cameron.
Oh, hey, Cameron. You know, it's funny. Cameron Sanderson is here, and then there's someone named Blake Cameron who signed up. Are you here, Blake? That was fun and confusing for a while. All right. So I guess I kind of want to, and forgive me, I don't have that other program. I guess I kind of want to talk a little bit about how the CRT itself actually sort of works. So if everybody's okay with that, I mean, it doesn't take very long. Just relax maybe, and we'll try it on the whiteboard and we'll see how this goes, and because there's a lot of misconception about how it works. So I'm actually going to start sort of in the middle of my normal presentation. Normally when I do a monitor presentation, I go through a bunch of setup first before I get to this point, but some of you are actually pretty experienced, and so here we go. So I want to start off by looking at the picture tube itself, the actual CRT, the actual picture tube itself. So as you probably know, the picture tube is made out of glass, and down here in the neck of the picture tube, there's something that's known as the electron gun. You know, and in my other program, boy, I had a thing with a slideshow, and I could show you a picture of an electron gun. If somebody wants to Google an image for the actual electron gun, you'll see what an electron gun looks like. But on the schematic diagram, the electron gun is represented by these three sort of backward L-shaped symbols for a color monitor. If you're a monochrome enthusiast, Seth, I'm sure you know there's only one electron gun in a monochrome monitor. So these guys are called the electron guns, and it's really called the electron gun assembly because there are actually 3 electron guns inside the picture tube. And there's one for each color, as you know. There's one for each of the 3 primary colors of light, as you know, red, green, and blue. And as you know, the monitor, when you do conversion kit, there are 3 outputs from the board, red, green, and blue. And these are what we call the video signals, as you know. And I don't mean to ever insult anybody. I'm just going to go over some basic stuff. So these are called the video signals, as you know, and they're just changing voltages. The higher the voltage is, the more that color appears on the screen. So for the amusement industry monitors, we don't really have like a real standard for that video signal, but we tried to establish a video standard at one point, and it never really happened. But typically, the way it works is that coming from the printed circuit board, if you give it about maybe 4 volts or so, if you give it around 4 volts or so, it turns that gun on eventually. If you give it 2 volts, it turns on the gun, but only like halfway. And, if there's a volt, maybe it's barely on. And if it's really less than a volt, that's really what's known as your black level. It's supposed to be off at that lower voltage. So as you know, as I'm sure you know, coming from the printed circuit board are the 3 wires coming off the JAMA, the red, green, and blue signals. So those are sort of, let's say, 4 volts. But those things have to be amplified first. We can't just connect those red, green, and blue outputs right to the electron gun itself. They're totally different levels, and it would blow up the board. You just couldn't do that. So in the monitor itself, there are 3 identical circuits in a color monitor, and as you probably know, they're called the video amplifiers. Let's see if you can see this. Cool. On the schematic diagram, I wish I wasn't a little backwards with these graphics. On the schematic diagram, they're shown as these triangles like that, and that's sort of that is like a universal electronic symbol for an amplifier. The inputs are on the left hand side of the amplifier, and the outputs are on the right hand side of the amplifier. And as you probably know, that's kind of universal for all. Wait, sorry, let me do a little video production here. Hang on a second. I wish it didn't splash that first. That's universal for all. This is the dramatic part. That's universal for all video amplifiers or all schematic diagrams. That is to say, inputs are on the left-hand side and outputs are on the right-hand side, and the signal itself moves from left to right across the schematic. So inputs are on the left, outputs are on the right-hand side. So we'll talk about those things a little later, but I want to get the video amplifiers. One for red. Sorry, let me finish the thought. 3 video amplifiers, 1 for red, obviously, 1 for green, and 1 for blue. And we'll talk about those, I think, probably a little later, although those are pretty straightforward circuits. And in a color monitor, you do have 3 identical circuits there. We'll maybe look at the circuits later, but you have 3 identical circuits there, so you can always compare what's happening in one to what's happening in the other, even with the power turned off, if you're just using your meter to check resistors and transistors mostly and stuff like that. You have 3 identical channels. If one is bad, red, green, or blue, it's pretty easy to tell which one's bad. So anyway, we'll get to that later. But what I really want to talk about is the CRT itself. So this is the important part. And as you guys are working on really old CRTs now, boy, the chances of it being an actual CRT failure are extremely good now. They really are. Just show of hands or type it in or say it. How many of you have a CRT rejuvenator, tester rejuvenator thingy of some sort? John does. Jay, yes. How many have the CR70, let's say? The Sencor CR70. You got that, John? The CR7000, maybe? Anybody? What's that?
I got 2.
The CR7000? Wow. So I sold it for $495 a long time ago when I saw the writing on the wall for LCDs, and I thought, well, who the hell would want to restore a CRT? And now I really regret that, man, because the CR7000, if you're lucky enough to have one, is and you know how to use it and don't get carried away, is spectacular. It will eke out every little bit of life from the electron gun. And I think later on we're going to talk a little bit about how you can actually boost the heater voltage in a CRT as a last-ditch effort to boost emission. That's like the last thing you can do is kind of boost that voltage up just by taking a wrap of wire around the core of the flyback. A lot of you know this trick, and we'll talk about that later. But let me get back to the actual CRT itself. So let's get back to the whiteboard. Is this working okay for everybody so far?
Hey, Randy, I just wanted to mention, if anyone else has a CR7000, I came across this problem recently. The relays inside eventually start getting sticky, and you have to replace them all. There's about 7 or 8 of them in there. They're tiny little relays by Siemens. Just shotgun them all.
Are they, do they stick from non-use?
So I'm not sure. I have 2 units. One of them is still factory and works great. The other unit is the one with the problem, and I fixed it by replacing them all. I have no idea how much use or little use it got.
Are they readily available?
Sorry?
Are the relays readily available?
Yes. You can't get the exact same one because, well, you can get new old stock, but they want an arm and a leg for it. But you can get compatible ones for like $7-8 a piece.
Right.
So what's the symptom?
The symptom is your CR7000 will kind of trip out. You will put it to a setting, and then the 3, I guess, red and green meters, they kind of just flip out. Like the whole you'll hear the machine, go click, 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 and the whole system just freaks
especially
out.
in cutout. The cutout is just, you move one dial, they all move. Is that the symptom?
No, it's you can actually hear the relays like freaking out when it's having that issue.
Okay.
Anyway, yeah, sorry to interrupt. I just wanted to mention
No, I will only interrupt to say that this is precisely awesome and fantastic. This interaction right here. It's exactly what I was hoping for because this is different than a stand-up class, although it's kind of sort of is. But and I love that. No, no hijacking problem whatsoever. Are you through? All right. So all right. So let me go back to the whiteboard here, and I'm happy this is working. Okay. So what's inside the actual electron gun, if you bother to look at it, is that these cathode thingies, which are represented by this kind of backward L-shaped things on the schematic, are actually sort of little cylinders. They're sort of little cylinders like this. And those are the actual cathodes. These are called the cathodes. This is not the whole, yeah, you can see it. This is not the whole electron gun. Drawn here is just part of the electron gun, and it's referred to as the cathodes. The definition of cathode is something that emits electrons. Something that emits electrons is called a cathode. So these are the 3 cathodes, and they're actually coated on the surface with an element known as barium. In order to give up those electrons, this metal cylinder, which is the cathode, is coated with a really thin little layer of this stuff called barium. in order to release electrons, the barium has to be heated up. But if you heat this stuff up, boy, it releases a big cloud of electrons. So down here inside this little tiny cathode, it's only a few millimeters in diameter.
Did y'all lose audio again? Or is it me?
No,
Yeah,
no, thank you. Yeah, speak up. There's a mute button on my thingy that I keep it. Maybe I should just clip it on so I can look extra dorky. That'll be good. Anyway, so there's this heater that goes up inside, and it's called the heater. It's really technically known as the CRT heater because, as you know, the whole picture tube itself is called the cathode ray tube, and this is the cathode part of the cathode ray tube. So it has this little heater that goes up inside. The heater goes up inside the metal cathode, but it cannot touch it. It must not touch it. It has to go up inside. If it touches the thing, it'll turn the gun on solid color. We'll talk about that later, and you'll see why that happens. It's called a heater to cathode short, as some of you know. And there is something you can do about it, even if you don't have a CRT rejuvenator. There's like a magic trick that you can do. We'll talk about that in just a little bit. So this barium has to be heated up. Anyway, so down here in the neck of the picture tube on the schematic diagram, let me just redraw this, is this thing called the CRT heater. And the CRT heater can be represented on the schematic diagram in one of a couple of ways. It can be represented on the schematic diagram as sort of a tent thing, like a house. I don't know what you want to call that, whatever that is, the pointy thingy. It can be represented like that, or it can be represented, and often is represented by like 3 little points, because we have 3 electron guns. So there are actually 3 electron gun heaters, and this is designed to work off of 6.3 volts. And it can be AC or DC. In some monitors, many of the monitors that you guys are working on, this is 6.3 volts AC. But it's not 6.3 volts AC at 60 hertz, as most of you know. It's not like the regular line frequency for those of you down under 50 hertz. It's not line voltage. It's 6.3 volts AC at 15 kilohertz or 25 kilohertz, depending on the operating frequency of the monitor, whether it's standard resolution, which is 15.75 kilohertz, or 25 kilohertz, which is VGA or medium res. So we'll talk about that kind of stuff as well. In some cases, this is powered by DC that's derived off of the switched mode power supply, and we'll talk about that a little later on as well. But all I want you to get out of this at the moment is that we have these heaters that heat up the cathodes. So there's the heater, and you know, we have color. Wait a minute. Hang on a sec. Let me see if I have a color pen. Hang on. Let's see. Oh, look at that. See, there we go. Color. So they're red hot, right? And they're designed to work on, and of course, that's the glow that you see down in the neck of the picture tube. When you look down in the neck of the picture tube and you see that little orange glow down there, those are the CRT heaters that work. So there's the CRT heaters, and here come the 3 cathodes. I hope this will work. Let's see. So there's one cathode there, let's say, and there's another cathode here, and another cathode here. I normally draw this on a much bigger scale, so I guess I should have moved the camera further back. Next class, we'll do it right. So anyway, so again, remember, those are the RGB sorry, the RGB, and I want to say RBG, and I'm very sad about that. For those of you that join me in saluting her, I'm very saddened by that. Anyway, and so on. So, so there's this part of it. Now, it's important to understand that the cathodes do not shoot out a beam of electrons. Remember that this is called a cathode ray tube, right? CRT, as you know, stands for, I may have to make this, I might have to move the camera. I guess I could do it in just a minute. It's called cathode ray tube because this electron gun shoots out a ray or a beam of electrons. So it's called the cathode ray tube, but the cathodes themselves don't shoot out a beam. All they do is release a cloud of electrons. The actual cathode, when it's heated up, just releases a cloud of these negatively charged electrons. It's called a space charge. It just releases a big cloud of electrons, which is, as you know from, I guess, junior high school physics, is the little negatively charged subatomic particle that orbits in crazy ways around the nucleus of an atom. So this is what we're dealing with, these little tiny electrons. But again, I gotta stress that the cathode doesn't shoot them out; it just releases them. So in front of the cathodes, in between the front of the picture tube itself, and the cathodes, is this thing that's these things that are represented on the schematic diagram by these dashed lines. And if you would like to refer to any monitor schematic diagram, you'll see these with a much better drawing than I'm drawing here. And so these are referred to as the grids. There's a number of them. We'll talk about them in just a second. This is called a grid. Do you see where it says grid here? No, let me just write it up here. Grid. This is called a grid. Now, it is not a grid in the sense of what you would think is a grid like that. It's not that. It's called the grid because electronically speaking, the very first vacuum tubes, which this is, did use indeed a grid like this, just a grid made of wire like this, in order to control the flow of electrons. So it's an electron gun, and it uses this thing to control electrons. So it's still called a grid. It doesn't look like that. And if you've ever taken a broken picture tube apart, you can remove, I recommend you do this. Bad picture tube, broken picture tube, take the electron gun out and beat the glass off of it and take the thing apart and really look at it, because what the grid really looks like is just a little thin piece of metal. It's, and I'm not much of an artist, but it's a little thin piece of metal, and there are 3 tiny little holes in the grid, one for each of the electron guns. And so that grid is this, let's see, are you seeing it? Yeah. That grid is this thing right here on the schematic diagram. And there are a number of grids. There's one important one that I really, really want to talk about. There's a grid known as grid number 1, G1. We're not going to talk about that. It's the control grid. You don't care about that for the moment. The important one is a grid known as grid number 2, G2. Oh, can you see down here? No, you can't. Yeah, no, you can't. Give me 1 second. Give me 1 second. Give me 1 second. Hang on. I'm just gonna enlarge my view here. Stand by. Figure out how I'm gonna do this. There. That's more better. So if you don't mind, give me 1 second. Let me just refocus. still connected? Everybody okay? Cool. Everybody cool? All right. So, oh yeah, there's most of the board, which I'm using vertically, but that's cool. All right. All right, I'm still on, right? Everybody okay? Good, good. And everything
good to go.
All right, thanks. All right, so let me just kind of redraw the CRT. Nice and big. Do I have it all? Yes, I do. Okay, awesome. So here, I'm not going to do it in color. So here are the 3 CRT heaters that go up inside the thing. Remember, those are made to work off of 6.3 volts AC, but it really doesn't care if it's AC or DC. It's just a heater. And remember too that that's the little that goes up into the cathode, which are the 3 little backward L shapes. So there's one of them there. There's one of them there. There's one of them there, and of course there's red, green, and blue. And these are the 3 video. Do we see this? Yes, we do. Cool. The 3 video amplifiers, identical video amplifiers. Sorry for repeating myself. Red, green, and blue. So remember that these guys just release a cloud of electrons. They're just going to sit there. They are just going to sit there. It doesn't push them out or anything. So in front of this thing, there's a grid. So the schematic representation of the grid is just a vertical line like this. And this is an important one for everybody because this is the screen grid. This is grid number 2. We're cool, right? Yeah. The screen grid. And as you know, on the back of the high voltage unit, except for like the G07 where it's on the neck board, ouch, there's this thing called the screen potentiometer. And the screen potentiometer is like the main brightness control, as you know. You know, you crank it up to the right and it gets really super bright, and you crank it all the way down to the left and it should go black. It's not an uncommon failure to have that not work properly. That is to say, moving the screen grid doesn't make it go all the way black or white. And the way it does it is by controlling the voltage on the screen grid, which, depending on the monitor, can be anywhere from 0 volts DC to, you know, kind of depends on the monitor. In some monitors, it might be as high as 300 volts DC, 350. Can anybody correct me on this? I don't measure it very often. Anybody have input on this? Anybody measure their G2 voltage? What is it normally? No? 5, 4, 3, 2, 1. No? John, no? No? Head shaking? No? Okay. You guys are cowards. You're not turning on your webcams. Maybe you don't have them. That's okay. I don't need to see you. I don't need to see you. It's fine. Okay. So the higher the voltage on G2, the brighter the picture is. So, I'm sorry. And what it looks like, actually physically looks like, is just a little tiny wafer of metal. It's one of the pins that goes out to the neck board that you connect to on the neck board to the CRT socket, and has 3 little holes in it, one for each color, one for red, one for green, and one for blue. So you're varying the positive voltage on this. Well, remember that opposite charges each other. If you remember anything about basic physics, opposite charges attract each other. It's the whole basis for everything. I'm sure you understand that. So these little guys are negatively charged. They are negatively charged. So these little electrons will be attracted toward this slab of metal, which is connected to G2. And the more positive it is, the more it sucks those electrons this way. Now, some of the electrons do hit the metal part of the thing because they are attracted to it. But this hole is precisely aligned with the cathode itself, and this opening is what's known as, and I don't have to get into it. You don't care. It's called a virtual aperture. Opening is aperture, right? So it's called the virtual aperture, and it really kind of marshals these electrons through its field, this field, and it is what propels the electrons toward the front of the screen. The cathode itself doesn't do that. It just releases them. And it's the positive charge on G2 that attracts them toward the front of the screen. Does that make sense to everybody? Does anybody have any questions about that so far?
Pretty good.
Okay, everybody okay in that, Ludo? Cool? Ludo?
Yeah. So I thought actually that the screen was the anode voltage. So I just learned something.
Oh, yeah, I'm about to. Oh, that's my denouement, Ludo. I'm building to this. Electronics can be suspenseful and interesting. That I'm building to that. You hang on. It's they all float down here. So we'll. Sorry.
When you turn the screen voltage, you're only turning that 0 to 300 volt DC, not the 27,000 volt whatever.
Oh no! Oh no!
The opposite.
No, correct. And that has to be very constant. That can't fluctuate at all. If the EHT, what we call the EHT, the very high voltage at the second anode, which I will get to now, fluctuates, the picture size fluctuates, and it goes in and out of focus, and so makes sense. Everybody else okay? All right. So here we go. So this thing shoots the electrons toward the front of the screen. Now, let me see where I'm going to draw this. So I'm going to just make a little room right here. We're going to leave this here. I'm just going to make a little room here. I'll make a tiny, funny shaped CRT. On the front of the picture tube, coated on the inside of the picture tube, let me make this a little more rectangular here. Coated on the inside of the picture tube, as you know, is the substance known as phosphor. Phosphor. Not phosphorus, but they're called phosphors. And there are 3 different colors of phosphor, as you know. Let me find my phosphors. Find my phosphors. R, G. All right. So they're coating the inside, and you can see this with a magnifying glass, or even if you throw a few drops of water on the screen while it's on, you can see these phosphors, which are generally laid down in stripes down the front of the picture tube, although some very, very old picture tubes might have dots called a triad dots. But these things called phosphors are laid down in stripes down the front of the screen, as you probably know. Sorry, let me get a red pen that works. So there's one kind of phosphor that glows red when it's struck by an electron. And there's another kind of phosphor that glows green when struck by an electron. And the third kind of phosphor, ooh, that's purple. It's not RGP. Hang on. Oh. There we go. Blue, sorry. Blue. So, those are the 3 inputs, red, green, and blue. And so it's repeated a lot across the face of the CRT, as you know. Just give me a second to just be dramatic and draw these guys in here. I'm not sure. How does that look on camera? So I'm sorry for it's really tilty. I should probably do this. Oh, wait a minute. I should do that. Hang on. Live TV. Hang on. Hey, that's more presentable. That's way more presentable. Okay, super. Anyway, so again, you know, the the higher the input voltage over here from, I mean, you could argue from 0 to 4 volts. You could even argue 0 to 5 volts, but in a video standards committee meeting that I attended for an AMOA meeting, which was a big standardization meeting, we tossed around all kinds of video standards, and Williams wanted more lines for Joust and Robotron for theirs, and somebody else wanted a different refresh, a different sync timing or something, and we never developed a standard. So whatever it is, anyway. And so the video amplifiers amplify that, and the output of the video amplifier is connected to the cathodes themselves. The electrons are released by the cathode, and they're attracted toward grid number 2, the screen grid. So they pass through the screen grid, through those holes, and they zippity-doo-dah out, and they strike the inside of the glass front of the picture tube. As you know, there's a real thick glass front there. So when they do that, they whack on the phosphor itself, and as you know, it has to be precisely aligned. You all know about playing with magnetism and the degaussing coil. I'm sure we can cover it later if necessary. But I really respect that most of you know really a lot of this stuff anyway. So a little bit of magnetism goes a long way in diverting the beam, but it's all lined up well, as we talk about convergence or something like that later on. Electrons whack against red, green, or blue. They're just lined up. They just brighten it up. So what happens from a physics standpoint, what happens from a physics standpoint is that these electrons are hauling buns toward the front of the picture tube because they were shot out of the gun. It's an electron gun. Let's keep some perspective here. It's called a gun for a reason. It shoots out things, and in this case, the bullets are these electrons. So it's the electron gun itself and G2, and there's a thing called a focus grid, as you probably know, in front of it, and that's the focus, other control focus. We're not really talking about that right now. So they have a tremendous amount of kinetic energy. It's not speed of light. It's not relativistic speeds. I don't know how fast it is, but it's freaking fast. But it's not like light speed. That isn't the way it works. But they have a lot of kinetic energy, and which, as you know from junior high school physics, kinetic energy is the energy of motion. Any mass that is in motion has this kinetic energy. It has inertia. So these electrons are itty bitty. They don't weigh very much, but they weigh something. They have mass. So they have kinetic energy. When they whack against the front of the CRT, they trade that kinetic energy into light energy, and that's what makes the phosphors glow. When the electron itself, how's this look on camera? There. So there's the front of the CRT. When the electron is shot out of the electron gun and it whacks against the front of the screen, it trades all that kinetic energy into light energy. I think that sorry, hang on. Sorry. Oh, this was meant to be dramatic and I blew it. Hang on. Yeah. I think you're all aware that there's a law of physics. I think it's a second law of thermodynamics. Could be wrong. I don't care. It's called conservation of energy. You can't destroy energy. You can only change it from one form to another. So in this case, we have lots of kinetic energy, and it whacks against the front of the screen and changes all that kinetic energy into light energy. I think you remember Star Trek 13, where Spock gets caught on the ice planet, and he has to use the phaser to heat up the. Well, never mind. Anyway, so conservation of energy. So that's what makes the front of the screen glow. Is everybody with me in this regard so far? Cool. Cool. Yeah, okay. All right. Unless I hear objections, let me go back to the whiteboard. I think the whiteboard is a little more boring
I
because...
have one question, Randy.
Yes.
Sorry, what is the relation between the three different phosphors and the three different guns? How do the color align, or how do the red electron gun shoots only to the red phosphor on the screen?
Boy, you're right on point, Ludo. Your questions are exactly right on. They're a little tiny bit too soon, but you're
I'm sorry, I
right there.
apologize.
No, I love it. No. Oh, no. You're my perfect student. No. If I'm doing this properly, just as you guys are forming the questions, I probably have the answer because I've given the same lecture about 10,000 times. So I'm not saying be quiet. I'm not at all. I'm absolutely not saying that. But let's carry on. I'll get to that, Ludo. Back to the board. Sorry, back to the board. Cool. All right. So when the electrons pass through hit the phosphor on the inside. When the electron hits the phosphor on the inside, the electron does not come out of the electron gun. If the phosphor came out of the electron gun, you'd sterilize yourself, and I don't think you'd want to do that with a beam of electrons shooting at yourself. So that isn't what happens. The picture tube itself is made of glass, as you know, and glass is an insulator. And in fact, it's special glass in the United States. I'm guessing in Europe as well. Ludo, are you from Netherlands?
I'm from Belgium, but I live in
Belgium.
Australia.
That's right. This is special leaded glass. There's a lot of lead. That's what makes it so soft. If you've ever made the terrible mistake of putting your CRT face down on your workbench without protection and gave it a little spin, and now you got this fuzzy little dot right in the middle, it's because the glass is extremely soft because it's full of lead. In the United States, it's toxic waste, and you are not supposed to just discard it with the regular rubbish. You really have to actually pay somebody, a recycler, to take it off your hands. Anyway, so the electrons do not pass through. What happens to them? They bounce off inside. The electrons themselves, let me erase this focus grid because we don't need to look at that. The electrons, once they have shot out of the electron gun, that's a stream of electrons, and they strike the front of the screen, trading their energy into light energy, from kinetic energy to light energy, they actually bounce off inside. That's the deal. They can't come out of the glass picture tube like that. They have to really bounce off. So once they've bounced off, they no longer have any energy at all. Imagine firing a bullet out of a gun and hitting some impenetrable steel wall, and it bounces off, and it has no energy. It's bounced right off. So the same thing is here. So these electrons are bounced off, but we cannot allow those electrons to remain inside the picture tube. If we allow those electrons to remain inside the picture tube, they will quickly form a negatively charged cloud down here. A cloud down in the picture tube. There's a bunch of electrons in here now, and quickly, within a couple of seconds, what we call the bell of the picture tube, the big part of it, let's put that down. The big part of the picture tube is called the bell for obvious reasons. The bell of the picture tube completely fills with electrons. Well, imagine that you are a tiny negatively charged electron and you want to shoot out of the electron gun and strike the front of the picture tube. If you see this huge negatively charged cloud, remember that opposite charges attract. We talked about that before, but like charges repel each other. like charges repel each other just like opposite poles of a magnet. If you try to put two of the opposite poles of a magnet, north and south, together, Mr. Hans, they attract each other. If you try to put two south poles together or two north poles together, it repels each other. Same deal here. Opposite charges attract, like charges repel. It's like the first law of electrostatics. Anyway, so the beam of electrons, as it tries to get to the front of the screen, can't make it. In other words, there's a cloud of electrons here. I'll just draw it as a cloud. It's really a cloud of electrons. And as the electron beam tries to pass through it, whoa, it's going to be repelled that way. Whoa, it's going to be repelled that way. It's going to go this way. It's going to go that way. It'll never strike the front of the screen. And unless it hits the front of the screen, you're not going to have any brightness on the front of the screen because it's all full of electrons here, down here in the bell of the picture tube. Is everybody with me so far on this? Okay. We're getting there. We're getting there. All right. We're getting there. We're getting to the point. Okay. All right. We're leading up to this. It's the drama and wonder of electronics, which I love. I just love electronics. I especially like CRT monitors. They're really interesting, wacky, really crazy. And I don't think I have to tell you guys anything how crazy they are. All right. So we have to get rid of those spent electrons, so to speak, after they've struck the front of the screen. If we don't, they will build up a big cloud down here, and this is where the high voltage comes in. I think all of you are aware that there's some high voltage in the monitor in the picture tube somewhere, and there is, as you know, and it comes from what most people refer to as the Flyback transformer. More on that in just a second here. So on the side or the top of the picture tube, as you know, there's like a little metal plug that's molded into the glass of the picture tube there. And as you know, this is called the second anode. It's called the second anode. Well, remember the word cathode. These are the cathodes down here. Do you see this? Yes, you do. Do you see this? Yes, right here. Remember, these are called the cathodes, C-A-T-H-O-D-E-S, cathodes, and they emit electrons. An anode is something that attracts electrons. So cathodes emit electrons, anodes attract electrons. So that's connected, as you know, through this heavily insulated red wire. I'll just draw it over here into what most of you refer to. Oh, can you see this? You can't. You don't see this here, do you? Hang on. Hang on. I'll bring a tripod next time as well. Stand by. There we go. Wow. Yeah, definitely not professional. Not professional at all. This is the edge of the table that I'm working on. All right. Anyway. So this guy, a lot of people refer to this as the Flyback transformer. Its real technical name, specifically if it has the controls on it, and it may have one or it may have two, its real name in the real professional world is IHVT here in United States America, which stands for Integrated High Voltage Transformer. Because it is a transformer, the aforementioned Flyback transformer that you all talk about, but it is integrated with some potentiometers and other resistors, which we will talk about later on, into this thing called the Integrated High Voltage Transformer, or IHVT. In some cases, it is just the flyback. Like in the G07, it's just the flyback, and the controls, you know, are elsewhere. The potentiometers are elsewhere, but you know, that's a really old design and stupid, and so they, you know, so they make it all integrated. In Europe, or at least in UK, it's referred to as the LOPT sometimes, which refers to line output transformer, which I don't know what frickin' line they're talking about there exactly, but they call it the LOPT, line output transformer. Hey, you in Oz, what do you call it down in Oz?
Flyback. And in Belgium, we call it THT, très haute tension.
Okay. So exactly, high tension, right? So tension is another word for voltage. It's the real word for voltage, really. I mean, we call it voltage, but it's really tension, isn't it? Really, like in French or whatever. So, but we can call it the fly. Let's just call it the flyback because everybody knows what I'm talking about here. So there's the flyback transformer, but keep in mind that this is way more than just making high voltage right here at the second anode of the picture tube. It's doing a bunch of other things, not only making the screen volt. G2 is called screen grid, which is maybe, you know, plus 350 or zero to 300 or 350 or whatever. It doesn't matter. It's not relevant. And then there's a focus grid, so it does that. But it also often derives the 6.3 volts for the heater. In many of the monitors that you work on, let me draw it this way. In many of the monitors you work on, most of them, unless it has a switch mode power supply, probably, maybe even some of those. In addition to making high voltage, the flyback transformer also makes what is sort of the equivalent of 6.3 volts AC, but remember it's not 60 hertz, and that goes to the CRT heater. I'm not sure how to draw this here. We'll just do it like that, I guess. So that also goes to the CRT heater. So it does other things, and as we'll see when we look at like the K7000 monitor, there's a 12 volt output from the flyback, and there's a 24 volt output from the flyback. So please, this is really important. Keep in your mind that the high voltage unit in lots of monitors, not all of them, produces way more than this voltage here, which is, to get to the point, about 1,000 volts for every diagonal inch of the monitor or so. So, in other words, for like a 19-inch monitor, that voltage right there is approximately 20 kilovolts or so. 20 kilovolts or so, and it is direct current, and it is positive. 20 kilovolts plus 20 kilovolts DC. Everybody with me so far? Cool, right? You know? All right, so here's the deal. Let me see if Mr. Hands works for this. I guess so. Let me see what you're seeing here. Coating the inside of the glass of the picture tube. Sorry, let me start over again. No. Coating the inside of the glass of the picture tube, and if you've ever broken a CRT, you've seen this. There's a conductive paint that's sprayed on the inside. It's sort of a charcoal gray. It looks almost black. And it's sprayed on the whole inside of the picture tube, and it's called Aquadag, as you probably know. It's called the Aquadag, A-Q-U-A-D-A-G, Aquadag. And it conducts electricity. It's a graphite coating. It's carbon. It's a graphite coating that is sprayed on the inside of the picture tube when they manufacture the CRT. when they first manufacture the CRT, before they stuff all the guts in it and do all that stuff, it's really two pieces. One piece is the bell of the picture tube, and another piece is the front bit, which has the thing that answers the question that Ludo asked about how they could be lined up, and I'll get to that in just a second. And they spray the inside of the picture tube with this graphite coating that conducts electricity, and it's called Aquadag. It's called Aquadag because it is, if you care, or you may not, it is, when they spray it on, what's known as a colloidal slurry. It's like if you make Jell-O before it sets hard, and it's all loose, and you know it's thick, more than just viscous, but not gelled completely. It's a colloidal slurry. Anyway, so they spray this on there, and then that's allowed to dry, but that is what is connected to the second anode. In other words, when I connect to that second anode there, I am electrically connecting to the whole inside of the CRT. Is everybody with me on the concept so far? Pretty cool? Right. Now, I don't have a picture of it here. Normally when I do this lecture, I have a monitor in front of me, right? But on the outside of the picture tube, as you know, it's like also charcoal gray, isn't it? It's blackish gray, and that's also Aquadag. But as you know, the Aquadag on the outside is not connected to the Aquadag on the inside. The Aquadag on the inside has 20,000 volts on it. The Aquadag on the outside is grounded. It's grounded, as you know, and you know that there is either like a cable with a spring attached to it, and maybe a metal band that connects across the CRT, or sometimes it's just some brass fingers. Which I don't like this system. It's very stupid. I think dangerous. Just some brass fingers that are kind of screwed on there and that are sort of just touching the CRT. I'm not telling you anything you don't know. And those connect to ground. They're not connected to the inside. The inside's not connected to the outside. The inside's connected to 20,000 volts. The outside is connected to what is known as the CRT. We say ground in the United States. In the entire rest of the world, it's earthed, right? It's called the CRT earth. I think, don't you, in Oz, do you call it the CRT ground or the CRT earth? Hello? Calling Australia? What do you call it?
Ground.
Ground? You do call in Australia? You call it ground?
I think typically ground.
And isn't one of my fellow Canadian citizens here somewhere? No.
Yeah,
Hello?
Victoria, British Columbia.
Oh, cool. Oh, nice. Well, Victoria, BC is. Oh, that's nice. Yeah, that's nice. I like that. It's a real nice place. But I live in San Diego. It's all cool on the West Coast, brah. You know what I'm saying? All right. So sorry. So listen. Anyway. So this is really important. This is super, super important. This, as you know, this CRT earth, this black wire, is connected to the neck PCB, the neck board that sits on the, on the neck of the CRT itself. There's a CRT earth there, or ground, whatever you want to call it. Let me just call it ground. And that is super critical that you connect that. If you don't connect that up in certain circumstances, depending on how everything is all mounted, powered up and such, the monitor still works perfectly okay. Develop static charge, and if you approach the monitor, and you touch like even what you think is the grounded metal frame, that static charge will jump right out and scare the shit out of you. So it's really important that that's connected. That's really connected. And here's the deal: everybody wake up. Everybody wake up, wake up, wake up, wake up. So now that you know the basics, here's the deal. Let me just kind of redraw this. Stand by, stand by, stand by. And this is the important thing. I think it's important to understand. This is the thing that I think people just don't understand. the electrons have struck the front of the screen. They have bounced off inside. We need to remove those electrons or they're going to form that big negative cloud there. And that's what the second anode voltage is there for. The second anode voltage is not there to attract the electrons toward the front of the screen. It's the job of the electron gun and the potential difference, the voltage difference between the cathode, we're getting to this, and the screen grid that propels the electrons out of the electron gun. It's a gun. You wouldn't expect to fire a gun and have to have the target suck the bullet toward it. What kind of a gun would that be? Hey, you guys, could you suck hard? I'm shooting at you. Suck the bullet toward you. Okay. So it doesn't. So it shoots them out. And remember that the whole inside of the picture tube is charged at plus 20,000 volts now. So those little old electrons are now sucked out of the picture tube along the second anode. Along the Aquadag, which is now charged at 20,000 volts, and out the second anode, and then they go into the high voltage unit, and eventually these things get passed to the ground here. Can you see down there? No, you can't. But eventually those electrons get passed to ground, and that's how we get rid of the electrons. The electron gun, this is to reiterate, the electron gun is not, I can't do that. Sorry, are you still seeing me? Yeah. The high voltage is not there to attract the electrons toward the front of the screen. The high voltage there is there to remove the spent electrons after they've struck the front of the screen and bounced off, because they don't have any kinetic energy anymore, but they have a negative charge. And as the electron beam tries to make its way out and strike the front of the screen, which it does have to strike it hard to make it glow, it can't do that, and you don't have any brightness. So the electron is sucked out of the electron gun, out of the Aquadag, out of the second anode, along the heavily insulated red wire, which is really a thin wire, as you know, with a crap ton of insulation on it, into the high voltage unit, and eventually, if you look at the schematic, you'll see it where it really connects to ground, and that's the purpose of that. Does that make sense so far? Everybody okay on that? Cool-o-matic? Yep. Okay, great. Okay. So, riddle me this, Batman. Please put on your thinking caps for just a minute. If you could I'm just going to ask you to really think, not just to be sitting there absorbing a passive lecture here for just a second. Oh, let me just redraw it. Nice. I just want to ask you to really think, where am I? I'm here. I'm going to make this real big so we can kind of tell what's going on. Heater. Let me get a new pen. Hang on. New pen. Oh, much better. The three cathodes. And remember, the cathodes are the little, this was way at the beginning, right? It's the little cylinder with the heater inside and the barium that lets the electrons off. So in front of this thing is the screen grid thingy, just to redraw it there. And it's connected to the, can you see that? Yeah. The screen potentiometer, as you know. So that's just, I won't draw it out. That's just a variable resistor, and that's what you're varying when you turn the pot. And so it's anything from 0 to 350 volts. So this screen can be anything from 0 to 150 volts. These cathodes are connected through, oh, do you see it? Crap, I gotta make it lower. Hang on. Oh God, I'm lame. Hey, first day, right? Oh, there we go. Does that work? Does that work? No, it doesn't work. Yes. Okay. Sort of works. Let's see. I go from here to, yeah, I can do this. All right. So if you look at the neck board of a monitor, I guess I should have asked everybody to have a monitor in front of them. If you look at the neck board of a monitor, generally speaking, especially on the era that you're working on, you see 3 big ass resistors on the neck board. And they're connected to each of the cathodes. They're these big old resistors. Typically, they're a couple of watts, a couple of watt resistors. And there are 3 of them on the neck board. They get warm. And, you may have touched them and said, whoa, is this supposed to be that warm? And yeah, it's supposed to be warm. So these guys are connected up to, can you see this? Sort of, you can see here. They are connected to what's known as the video B+ in many monitors. The main power supply is referred to as the B+ power supply. We're not talking about power supplies now. There's another power supply that powers specifically what we're talking about here. It's called the video B+, and typically, let's say it's I don't know, just for the sake of discussion, it really doesn't matter. It's 125 volts DC. Just for the sake of discussion, and it really doesn't actually matter. 125 volts DC. All right. So when there is no video signal present on these things, the voltage at the cathodes is really about 125 volts DC or so. Well, the cathode's heated up, and this little tiny electron boils off the cathode like that. Imagine that too. Use your brain here. We're going for this thought experiment. That the voltage right here at G2 that you have set that about mid-level, which is where you kind of like to keep it mostly, and let's say that its voltage is plus 125 volts DC. It is also the same voltage. They are unrelated power supplies. They drive 2 completely different ways. Well, I shouldn't say that, actually. I'm sorry, I misspoke. But it just happens to be 125 volts there. Think about this for just a second. If I was a little negatively charged electron, would I feel inclined to move in either direction? Here I have 125 volts of potential, right? Of voltage right here. Here I also have plus 125 volts of voltage on the cathode itself. If I'm a negatively charged electron, yes, I'm attracted to positive. But if these things are equal, that electron has no place to go. Does that make sense? Everybody cool on that, right? So at this point, this thing is in what we call cutoff. It's cut off. That electron gun is cut off. It's not going to emit anything. Now, though, well, we don't want a blank screen. We want some nice bitchin' ass game in there. Oh, sorry, this nice game in there. So let's increase G2. Let's increase the screen voltage. And as we turn it to the right, the voltage on G2, the screen grid, the most important grid for you right now in this discussion, G2, we increase the voltage. I still have 125 volts here, but now I have a higher voltage here, so it's going to attract the electron toward G2, which you remember has holes in it, 1 hole for every electron gun. And the higher the voltage, the higher the potential, the voltage at G2, the more profoundly that works. That is to say, you get more and more. I'm actually not sure if they move faster and faster, or you get more and more electrons coming off. The beam current increases, so I guess it has to be more and more electrons. Maybe the the speed doesn't change. I don't really care. But so the higher the potential voltage at G2, in other words, the more you turn up that control, which is clearly called screen grid on the high voltage unit there, what you're really doing is changing the voltage on G2, you're increasing that, and the higher the voltage, the more the electrons come out and the brighter the screen is. Does that make sense to everybody? And again, what my point is, the high voltage is not attracting the electrons toward the front of the screen. The high voltage is there to suck them out after they've struck the front of the screen. I guess I should draw that in. Second anode to high voltage unit. It's this system right here that I just described that propels the electrons toward the front of the screen. So here's the way. Now you all know that, right? This basics are over. Is there a timer on this thing? How long have we done this? How long have we been connected? Whoa, an hour and 23 minutes. I can't believe it. Really? God, that went fast. Hang on a sec. Hang on. I didn't realize. Wait, let me be dramatic. Hang on. Hang on. I didn't realize I'd be spending so much time on the whiteboard here. And again, with that other program, I could do a split screen and stuff like that, and you could see myself, I suppose, as you're seeing me here, and this at the same time. So sorry if this is a little boring looking at the whiteboard. But if you were sitting in a classroom, I suppose you'd be looking at your cell phone, which you can do. I don't care. All right. So let me get to the point here, and back to that camera. All right. So the three cathodes are. Oh boy, I didn't leave myself much room here. The three cathodes, they're each connected to the video output transistors. Those are the three big ass. Well, they're not that big. Can you see that? Shoot. Okay, I'm not going to redraw the whole thing, but I do need to move over. This won't make any sense to you, by the way. I'm so sorry. I don't mean to be unprofessional. Hang on. Here. Okay, so on the neck board, as you know, there are three video output transistors in a typical one, most of them. And these are three identical NPN transistors. I hope maybe you know something about transistor theory. A transistor is just a switch. So, and I'm really kind of simplifying this. So the emitter of these things, that lead is known as the emitter. It is typically the lead, not always, but typically the lead that's on the right-hand side. Over here is the emitter. And it's just the name of one of the things. It's called the emitter. The other side here is called the collector. And when the transistor is turned on, the collector and emitter connect together. And when it's turned off, they're not connected together. And I hope that makes sense. And the thing that turns it on and off, as you likely know, is the one connection on the left-hand side here. And that's known as the base of the transistor. So base, collector, emitter. Don't ask me why it's called the base. It has nothing to do with physically what it looks like. It's just called the base. I'm just a changer. I got no idea. Anyway, so this is the thing that's connected to the rest of the video amplifier circuitry, the red, green, and blue. We'll just look at red, which doesn't fail very often. Your mileage may vary, but the electronics itself of most of this circuit doesn't really, in my experience, I guess, fail very often. Anyway. So this thing just puts voltage on the base, typically 0.7 of a volt, or we don't really care. Put voltage on the base and it turns the thing on. And remember that this guy, and you should know that this guy is connected to the actual cathode that's inside the picture tube. That's coming out fine. So that's the cathode that's inside the picture tube. And the big resistor, typically it's like a 2-watt resistor. I still didn't leave myself enough room. Hang on. It's connected to the cathode, and it's connected to that kind of 2-watt resistor, and we don't care what the actual resistance is. Oh, it's still low. And that end of it is connected to that thing that I mentioned before, known as the video B+. I'm so sorry I sucked so much at this. Hang on. Definitely gonna have a tripod next time. I thought I'd get away with it this time. There. Oh, there we go. Beautiful, beautiful. All right. There we go. Right. So that's inside the picture tube itself. This is video B+, which remember is, let's say, plus 125 volts DC, and that's not adjustable. It's just that's the video B+. And so that's inside the picture tube. Here it is. So put on your thinking cap here again. So grid number 2 is in front of this guy, and that's what you use to control the main brightness. When this transistor is turned on, it makes the gun turn on more. That makes sense, doesn't it? When that transistor is turned on, the more the video output transistor is turned on, the more that electron gun is turned on. And the important thing is this. The lower the voltage is on the cathode, this is the cathode, often abbreviated with the K, by the way. If you look at, can you see that? Yeah. If you look at the picture tube neck board on a picture tube, and you see the horseshoe arrangement of socket pins, it can be labeled stuff like GK, green cathode, or it may say KB or KR, cathode red or green cathode. Not to confuse C for cathode with G for C for common. And so we abbreviate cathode often with the letter K. Sorry, let me get a drink. Hang on. Plus, I think any German speakers here, don't you spell cathode K-A-T-H-O-D-E in German, I think? Ludo, you should speak every language. You're Euro. Oh, are you cold, Ludo? Why don't you turn up the heat, bro?
It's 6 a.m., mate.
I'm so sorry. I'm so sorry. You needed a bigger pot of coffee, right? All right. So the deal is that because you're trying to increase the potential difference, the voltage difference here, the lower the voltage is on the cathode, the more that gun turns on. When you give it a high positive voltage coming into this thing on the left-hand side, the 0 to 4 volts or whatever, the video, the RGB from your JAMA connector, it is really making this go lower. The higher the voltage coming in, the lower the cathode voltage goes. So that seems counterintuitive, doesn't it? And that's my point. How on earth would you ever in your mind think that the lower the voltage is, the more something turns on? But this is actually the way it's done in electronics in general. We kind of have a name for this. This is, I'm simplifying this quite a bit. This is known as the ground switch. This is known as the ground switch. And what it's doing is switching this ground in and out. When the transistor is not on, this resistor, can you see this? Yeah. This resistor pulls the voltage up. We call it a pull-up. It pulls the resistor up to the 125 volts. That is, remember, this is important. It's called the video B+, the video B+. And we're going to talk about where that's derived, in just a little bit. So when the transistor is not on, the cathode voltage floats high at about 125 volts. And remember, if G2 was set for 125, you would have a black screen, which is kind of where you want it set. You don't want to see the raster in the background of the game. You need the background raster to not be there. You just want game to show. So so it's in cutoff, and then when you turn this transistor on by putting positive voltage here, it actually makes the voltage on that pin right there, the cathode pin, of red, green, or blue, whichever it is, pins, whatever, 6, oh my God, mind fart. I can't remember the pins. Anyway, it varies somewhat, but not much. So it makes that voltage lower. It makes the voltage on those pins lower. So is everybody with me on it? It does seem weird, but it's the way we do it in electronics. And again, it's kind of known as a ground switch, although this is not exactly, it's kind of a perversion of the ground switch. But it is. So lower voltage equals more brightness. That's the deal. Does all of that make sense to how that video system works so far? And I'm getting to a failure coming up. Everybody okay? Everybody okay?
Yep.
Any questions so far? Oh, who needs to leave? Seth? See, oh, he's gone. Well, sorry. I said it was going to be 2 hours. I'm offended. All right. Okay. So here, so here we go. So the first question was, is that the guy that, are you still here, person that had it dark on the left and bright on the right, or was that him that left? Oh God.
No, that was me.
All right. All right. Okay. So here's the reason behind that, and that is this. I told you previously that the flyback transformer, the high voltage unit, creates more than just the high voltage. There's a high voltage winding on the thing, and that goes to the second anode, and that's, you know, like the 20 kilovolts or whatever it happens to be. And there's also another winding on this thing that produces the sort of the equivalent of 6.3. Can you see that? 6.3 volts AC. Shoot. And I say the equivalent of 6.3 volts AC because if you try to measure that on the heater pins, there you have the pins, typically pins 9 and 10, as you know, are labeled H for heater, H for heater. If you try to measure it there, you typically won't reach 6.3 volts AC because this is happening super fast at 15.75 kilohertz. As you know, the horizontal frequency, some monitors you can hear that high-pitched squeal. You know, I think you guys probably know some basics about how the monitor works. So the flyback's operating, it's AC because it's a transformer. But it's operating not at 60 hertz or 50 hertz. It's operating at, 15 kilohertz, like that. So if you try to measure it with your meter, it depends on your meter. It may, I can't even predict what it'll show. You really don't even know. Even the highest quality fluke meter, not the highest quality, but even some handheld flukes won't read it. Anyway, but in addition to that, in some monitors, not all of them, there's another winding on the flyback transformer that is the video B+. It's where it's derived. So there's 125, just to make this simple, there's 125 volt AC winding on the flyback transformer. And there is a high frequency diode. These have to be fast recovery, high frequency diodes. Typically they look a little larger than like a 1 amp diode. They look like they're about 2 amp size, but they're kind of big because they're these special fast recovery, high frequency diodes. You can't put conventional diodes in there. They have to be these fast recovery diodes. Not a common failure. I don't know. Contradict me if your experience is different, but not a big failure. Anyway, but here's the failure. And that is that we have to turn this AC into DC. The video B plus is DC, it's direct current. So as you probably know, the diode changes it from AC to DC, and following the diode, always there's your nemesis or your best friend, depending on how you look at it, the electrolytic capacitor. You know, I'm a technician. I get paid to fix stuff. I love the electrolytic capacitor. It's job security for me. I mean, it's fun for me. It's fun, honestly. Wait a minute. Let me change camera here. Hang on a sec. Honestly, for me, as a technician, I think it's more joyful and interesting to find the problem, the bad capacitor, and replace it, or capacitors, and replace them and have it work. But I do understand, and I recommend putting in cap kits. But I mean, you know, you all say that. Oh, well, whatever your problem is, put in a cap kit. And many times you laboriously put in this entire 32 cap kit, and in the end, you have the same exact symptom as when you started, and it turns out to be X, Y, or Z, something that if you understood the basics of, perhaps like what I just went over, it would help you pinpoint the problem. And isn't that maybe more rewarding to your hobby, or is fixing the monitor just ancillary to your hobby? Your hobby really is playing the game and getting it all restored. If you could snap your fingers and have the monitor be fixed, would you? What's the fun in that? You know, I mean, if you had an HO train set and you could snap your fingers and it would be done, well, it's not fun to operate the train. Well, I'm sorry, and I don't mean to disrespect people that play, because I'm not a gamer. I know you guys do. Anyway, so that's my philosophical deal. So, getting back to the real point of this, just to get back to the board here. I hope I haven't lost everybody with a bit of a rant. Not that much of a rant. Anyway, so this is where the video B plus is derived. Now, this is the flyback transformer. And as you know, the way a monitor makes an image, I'm really getting to the meat of it here. So the way the monitor makes an image, as you probably know, I just hope to God you don't. I mean, you do. Is that it draws a line from left to right, as you probably know. The electron beam itself sweeps from the left-hand side of the screen to the right-hand side of the screen. Each one of these things is drawing a line. It's called a line of raster. It's a raster line, or a line of raster. When the beam gets to the right-hand edge, it's turned off. There's a whole circuit that does that. We're not talking about it now. It's called the blanking circuit that makes the beam fly back to the left-hand side. And you know that it has that magnetic yoke. That is not what we're talking about now, so don't worry about it. That controls the sweep of the electron gun that sits on the neck of the picture tube. So the beam is turned off, and then it quickly retraces back to the left-hand side, where it draws another line from left to right. So it only draws these lines from left to right. This is the important thing. And that's the horizontal direction of the monitor, as you know. The monitor is wider than it is tall. And the wide direction is always called the horizontal direction, as you know, regardless of the fact that the monitor might be mounted vertically in the game. The wide direction is still called horizontal. And as you know, the short direction is called vertical. Whoops, V-E-R-T-I-C-A-L, vertical. All right. So the flyback transformer in yours always, I guess, is really driven by the horizontal deflection circuit, as you probably know. The same circuit that makes the beam move from left to right, the horizontal, it's called the horizontal, can you down here? Yes. The horizontal deflect on ION, sorry. The horizontal deflection circuit causes the beam to be deflected from left to right, and it makes this line go across the screen. So it's the horizontal deflection circuit. It's the horizontal deflection circuit that also drives the high voltage unit. The flyback transformer that's in the high voltage unit not only makes the beam move left and right, but also drives the high voltage unit itself. It drives the primary, what's called the primary winding of the flyback transformer. And if you don't understand that, don't worry about it. And I'm not going to get into transformer theory at the moment. You don't really care about. Just realize that the horizontal's driving that, and the horizontal frequency is this 15,750 hertz I've been mentioning on and off, or in your medium resolution monitors, as you know, 25 kilohertz is what we call the horizontal sweep speed, or the horizontal frequency. So that's what's driving this. In other words, what comes out of the flyback transformer, every time it makes the sweep from left to right, it is also sending a pulse, a momentary pulse, out of that what's called the secondary winding on this thing. The diode rectifies that and changes it into direct current, but then you have to have an electrolytic capacitor. I'm not getting into power supply theory, but as you know, change of capacitors, electrolytic capacitor failure is really big, and this is a power supply. And this is the filter capacitor for that power supply. So its job is to, let's see where I'm going to draw the graph here. Its job is, let's see if this works. Yes, kind of. The capacitor's job is to keep the voltage at 125 volts DC. Can you see that? Yes, you can, right? So you have 125 volts DC. And what I've drawn here is a simple graph that shows time in the horizontal direction and voltage in the vertical direction, time versus voltage. So that's what DC looks like on a graph like this, which is the same graph that an oscilloscope draws. All an oscilloscope is doing is drawing a graph of time in the horizontal direction versus voltage. The more voltage, the higher the line. So 125 volts DC. 125 volts DC. So if that capacitor is good, everything's good, you have 125 volts DC there. But here it is. Here it comes. Here it comes. We're wrapping it up now. If this capacitor fails, instead of keeping the voltage at 125 volts DC pure and constant, it will drop in between pulses. This is a series of pulses coming at 15 kilohertz, and between every single pulse, it will drop the voltage there of the video B+. Well, remember that the lower the voltage on the cathode, where are we here? Hang on. Drama ensues. The lower the voltage on the cathode of the electron gun, remember, the more brightness you have, the more that gun turns on. Low voltage equals high brightness. If, as this capacitor ages, and it's one of those ones that you just automatically replace, you don't know why you're replacing it, you're just replacing it. As it ages and it allows the voltage at the cathode to drop, the video B+ voltage to drop, it makes the brightness higher. Therefore, on the screen itself, or let's call that the screen itself, the screen is dark on the left-hand side, and as the beam travels from left to right, it gets bright on the right-hand side. And you're almost always assured that if everything used to be I'm sorry, wait, wrong camera, sorry, I forgot, sorry, hang on. I should just do this, hang on. Let's see if this works. Okay, yeah, hey, that works. So so you have it's dark on the left-hand side and bright on the right-hand side, as that capacitor ages, it allows the voltage to drop, and that's why that happens. So if you really want to zoom in on a problem and you just have this one issue, other than that, it looks great. Your geometry is good. That is, it fills the screen. The sides are not crooked. It's all square and beautiful and all that kind of stuff. Don't you just want to change one capacitor instead of laboriously changing all these capacitors? And I see some of you have horizontal failures and you're messing around with the vertical. It's like, why are you even looking at it? You shouldn't even be screwing with that. Every time you touch a soldering iron to the board, you're risking something. I'm exaggerating. I want you to be professional, but so that's that. So this electrolytic capacitor might be, and sometimes is, mounted on the neck board itself. You just see usually like there's one electrolytic on there. It'll shock the shit out of you if you get across it. It's 125 volts when it's on, and sometimes it's down on the chassis. But typically, you really want to have a filter capacitor as close to the load as possible. The filter capacitor is connected between the output of the power supply and the load. You really want the source, the capacitor, to be as close to the thing that's actually going to use it, the load, as you can possibly have it. So often it's mounted on the neck board. Sometimes there are two. So that's the one you're looking for. If it ain't that, hard to say. But anytime something is sort of, this is another important thing to know, that anytime something is sort of working, but it's in some way distorted, like bright on the left, dark on the left and bright on the right, you're almost guaranteed to be looking at a capacitor failure, aren't you? I mean, it just is that way. It's, everything. If you have a semiconductor failure, typically the thing just doesn't work at all. You have some sort of catastrophic failure. If you have an open resistor, usually something just doesn't work at all. But when capacitors fail, especially as you watch them fail over time, or when you turn the machine on in the cold basement, it doesn't work, and then as it warms up, it starts to work, you're really almost guaranteed to be looking at a bad capacitor. So, makes sense sort of as to have spent 2 hours with me looking at?
Yeah, that was awesome.
Yeah, that's awesome.
Yeah, thanks, Randy. It was a perfect explanation.
Okay, super. Can I give another plug to my Patreon account? You absolutely don't have to do it, but this is an experiment, and a social experiment, and I guess I'd be a fool if I didn't just point out that I got that Patreon page, and I don't know how to get there. There's a link somewhere. And that's all. Anybody have anything to add?
Just quickly,
Yeah.
Randy, getting back to the tube theory, the shadow mask or aperture grill. How does
Yes, I didn't get for that for Ludo. Sorry. I can do that in just a couple of minutes. I'm sorry. Finish voicing your question, and I'll get to that.
Oh, that's all it was. I just wanted to see how that fits into things with the phosphor and.
Oh, okay. So sorry. So yeah, I have a few minutes. So thanks. I guess just to complete the thing, I should finish that. So, the electron gun is this thingy. It's in the neck of the picture tube, and here it is. It's really impossible to align the electron gun perfectly. And what's called the purity and convergence procedure is fairly involved. We can maybe talk about that some other time. But it's the electron gun. It's just a barrel that looks like this with 3 holes in it. Is just more or less kind of aligned with this thing. So this is really one of the most fascinating parts of CRT construction. On the inside of the picture tube, before the glass on the inside, before that phosphor that's painted on the inside there's actually a metal screen there. And it's called the shadow mask. It's called the shadow mask. and it's actually a piece of metal, and and you can look right through it. If you take one out, it's just like looking through a window screen. You can see right through it, and there's one hole in the shadow mask for every phosphor dot that's on the screen, for every triad, for every group of 3 phosphors. There's what's called a triad, because there's 3 different phosphors. There is a hole, and it's like a really super sharp hole. It's stamped out of this piece of steel, but it's what gets magnetized when you hold a magnet next to the picture tube and you take the magnet away, and the colors are all messed up. That's what you're really magnetizing, is this thing called the shadow mask. And what's really amazing is that phosphor is sprayed on to the inside of the CRT through the shadow mask. And that shadow mask is mated to that picture tube for life. They're not interchangeable in any way. At the factory, they temporarily mount the shadow mask in there. If you go on YouTube and look, you'll see there's some YouTubes on this. And they spray one color phosphor on there. Then they take the shadow mask off, wash the shadow mask off, snap it back in place. It just snaps in place. Spray the next color phosphor on, take it off, wash the shadow mask off, do that with the third color, take it off, mount the shadow mask on there, and then they glass weld the thing together. Then they suck the oxygen out of the end of the picture tube through the glass nipple, and then they seal it, and then it's a vacuum tube. But you may have noticed that if you've ever taken an electron gun out, it looks like this. There is a long metal piece that kind of dangles off the end of it, and it actually is touching touching the Aquadag on the inside, on the inside of the picture tube. And that little thing happens, you don't have to know this, it happens to be called the getter. When they, G-E-T-T-E-R, getter. Oh, you probably can't see that here. Getter. It's called the getter, G-E-T-T-E-R. When they first manufacture the picture tube, they suck as much of the oxygen out of the nipple end as they possibly can. They seal it off, but there's still a few molecules of oxygen floating around there. But we can't allow that to float around inside there, because as the electron beam shoots out of the electron gun, it'll hit this gas and it'll ionize the oxygen, or any gas that's in there really, but the oxygen, and it'll burn up it'll cause it to glow on the inside, and it'll also burn up the heater down here. So we don't want it to glow on the inside. We just want it to glow on the outside. So this getter is actually filled with flash powder. I mean, I sort of hope you break a picture tube in a way. I don't really, but and take a look at the getter, and you'll see that it is filled with flash powder. There's like flash powder on the inside of it, just like an old-fashioned photographer used to use in the Wild West and take a picture with flash powder. And so when they first manufactured the picture tube, they suck all the air out, but then they use an inductive heater at the factory to flash that off. An inductive heater, they just hold the induction coil next to this thing. It gets red hot and boom, burns up the remaining oxygen. It's called the getter because it gets the oxygen out. Weird thing to call it for that reason, but so it kind of makes it a hard vacuum inside there. But I mean, just to reiterate, sorry, this is the camera. Just to reiterate this concept of the high voltage not sucking the electrons toward the front of the screen. Remember, that's the job of the electron gun. Here's yet another way to prove, I guess, in your mind that is not what happens. The Aquadag here is connected to the second anode. So the Aquadag on the inside is at 20 kilovolts, or whatever it is, plus 20 kV. And so is the final ring on the outside of the electron gun, which is called the acceleration grid. This metal piece here is attached to the thing on the end that is just a hole. It's just a a circle of metal. It just looks like that. Basically, it's a how do you like that? And it's also charged at 20. So the potential, the voltage, is the same between here and here. Well, if the voltage is the same, there's no way it could be attracting something one way or another, could it, right? If the potential is the same here and here, it's the same as if our previous discussion about the electrons moving between the cathode and screen grid, right? If the potential is the same, the voltage is the same, they're not going to move. So it's impossible for that to be what's happening. The high voltage can't possibly be attracting the electrons toward the front of the screen due to that physical and electrical construction. There you go. Sorry. So anyway, so the aperture grill here, this thing, there's a hole for every electron beam here, red, green, and blue. And if let's say this is a hole here for the green. Here's the green. It's the one in the center. It goes right through. But if the red tries to hit it, it can't. It hits the metal. If the blue tries to hit it, it can't strike it, the front of the screen. It hits the metal instead. So that's what you're aligning with those rings, as you know, the deadly rings, the purity and convergence rings, the things with the plastic tabs that are all broken off on all your games. Boy, as you probably have found out the hard way, when you mess that up, oh, yeah, you might never get it back. Oh, it's really a bear. And I'm not Mr. Purity and Convergence. Well, we could talk about it, but I've had not such good luck doing that. We can certainly talk about that. So that's the point of the shadow mask, and it's what's called the aperture grill. That is to say, the aperture is a certain opening there, and the whole thing is called the shadow mask. The grill is the holes that it goes through, and only one color at a time can strike it. And by moving those rings around, moving those rings around on the neck of the picture tube, you align where the red, green, and blue guns go. I hope in your lifetime you never have to do that. Maybe you've been successful. Cool. Anything else? Any other questions? We're coming to an end here. Yeah, I think we're out of time. Yep, exactly 1:59. Awesome, good timing. And thanks everybody. You know how to get in touch with me. Get in touch with me at Facebook or send me an email. And I'll somehow let you know where this recording exists. Okay.
Thanks, Randy.
This was awesome.
You're welcome. My pleasure. Right. Bye-bye.
Thanks, Randy.
Thanks, Randy.